everyone, and welcome to another video of CS202. Today's topic is going to be virtuals, but before we get there, I would like to cover copy constructors as well. And so let's just go ahead and get started. So that, rather than trying to explain what virtuals are, I'm just going to show you when we get there. But first, let's look at copy constructors, because that's one thing that I'm not sure I've covered yet, and I want to make sure that we are on the same page with that. So normally when you're making a class, so let's make a little sample class here. Let's call it class A. And so let's say our class A has a variable. Let's make it just a normal variable first, okay? And then we'll come back and modify the example. So it has a variable x in it. And so if I want to make a constructor for this, I know that I can make a default constructor like this that has no parameters. I can also make a constructor that's like non-default that has some parameters in there. So like, let's just say int I, and then I know that I can initialize values based on those parameters, right? And that's one of the main usages of that. So that's another type of constructor. Of course, there is one more type of constructor, which is what I want to talk about today, and that is known as the copy constructor. And so normally when you're making a class for, let's call this example, so let's just like, let's put this one to be red. Okay, so whenever we want to do the red constructor, we know we make an object like this. We say class, or we don't actually put the word class in there, but you put the class name, and then you put whatever it is. Let's just call this like A1, and then bam, it uses the default constructor. Now the default constructor maybe initializes x to be equal to 0. Okay, so if I go and say a dot cout a1.x, I know that I'm going to get back a 0 because it's a public variable and it has a 0 in it. Okay, now let's say, for example, that we're going to be doing the purplish looking one here. So for that one, what it would look like would be something like a2 5, and what this is doing is it's passing a 5 to the I variable, which is initializing the value of x with 5. So now if I go ahead and say cout a2.x, this is going to get us a 5 in comparison to the 0. Okay, this is what we know so far. Now the third scenario, let me just make sure we remember that the third scenario is going to be this new constructor that we're going to make, which is known as a copy constructor. And that is in the scenario that you wanted to do something like this. So I say we wanted to make a third object, but rather than initializing it to 0 or initializing it to 5 or whatever, we want to make a copy of an existing object. We want to copy an object. Well, you can go and write this syntax. So in this syntax, what is happening is I'm making a brand new object called a3, but as the parameter for the constructor, I'm actually passing an object of a different one, in this case a2. Now what this is supposed to do is it's supposed to take the contents of a2 and make a copy into a3, into the contents of a3 basically. So if I go ahead, actually, well, let me finish this, and then I'll code you an example so you can see that. But here, let's finish this paper example. So the idea here is we want to copy the contents. Now, if you do this without writing a copy constructor, kind of like the default constructor, if you don't have one, you get one anyways. It's just like, in this case, who knows what's going to be put on X. So if you want to make a custom copy constructor, which I'll show you why you have to in certain scenarios, what you do is you go ahead and you write your constructor as you normally would, but instead of putting it like some random parameters here that, well, not random, but parameters like int to initialize an int, you're going to put one parameter, and that parameter is going to be the same object type. And then just put some identifier that you want for it. So let's just call it old. Okay. Now, one more thing you have to put for this is you need to make it a const. Remember what the const does for a parameter? It makes it into a read-only. And so, because it's read-only, basically, you don't accidentally modify the source object that you're copying over. Okay? So now, what do you put inside of this constructor? Well, you can actually put whatever you want. But the idea is you want to do like a member-wise copy. So in this case, there's only really one member, which is x. So what you want to do is you want to take x here, which is the x from this new object you're making, and you want to assign to it the x from the old object that you have, which I conveniently called old. Something like that. Okay? So this normally happens by default. In fact, I don't actually need this piece of code here, this whole stuff. I don't need it for this to work for this specific function. So then you might ask yourself, what's the point of you showing it to us? Well, I guess if in theory, when you wanted to make a duplicate, you wanted to do something else, you could. But more importantly, the game changes when you're using dynamic variables. Okay? So for that, though, I would like to switch over to the computer. Now that I wound up the VM here, to show you that, so that we can actually see the differences. Okay, so switching over to the VM, let's go ahead and make our class A, but this time let's modify the class a little bit. Actually, first let me just make it the same way, just so that you can see it in action. So we got our int x and we got our default constructor. Let's put I'm going to put a 10 instead of a 0. Okay, and then the other constructor, which is, and by the way, I could have combined these two constructors together, right? Like I could have done something like a default constructor by just putting a default parameter here, but I didn't do that, which is, it's okay. Just like instead of doing this, I could also just make it into the body of the function by doing something like this, right? But I chose not to do that either. There's a lot of ways you can code the same thing. It's the power of coding, right? So now let's go ahead and make our copy constructor. So again, it's going to be like any constructor has the A, this because it's the name of the class, and then we're going to make it a read-only parameter by putting the word const. It's the type of the object you're actually creating, and then go ahead and pass by reference. So now in here, all I'm doing is I'm saying x, and I could also be explicit like this, but it's kind of pointless. I will talk about the this pointer in a minute though, so we'll get to see that. But for now, just say x old gets x, or x gets x old actually. So, or old x technically. Yeah, so the reading this line correctly is saying x gets old x. There we go. Okay, so now if we go ahead and run this, so let's go ahead and make some objects with a1, a2 with a 5. And then let's make an a3 without anything. Oh wait, no, we already have a1 for that actually. So we don't need that. Let's just jump right in and make a2 out of a3. So now let's go ahead and just see out all of them. So a1.x, a2.x, a3.x. We're going to need some spacing for these things though. Okay, fair enough. That should look okay. All right, so run it. Don't worry about that, just run it again, and we're good to go, okay? So you can see that A1 gives us a 10 because it's using the default one. A2 gives us a 5 because that's what we set it to here. And as you can see, A3 is in fact also getting a 5 because it copies it over. More importantly, to make sure that this is okay, I'm going to go ahead and modify A2's X and change it into a 7. I want to show you that this is actually a deep copy as it is. Well, it's a deep copy because we don't use any dynamic variables. So, and this is, it's actually a copy of it. It's not like some aliasing and whatnot, remembering from the shallow versus deep copy issue, okay? So you can see that it is truly making a copy of it. We can change A2 and A5 remain, and 5 remains in A3 because we assigned it that way before we did the change. Okay, so they're independent copies. It's a deep copy per se, and everything is nice. Okay, cool. Now comes the issue that let's go ahead and instead of making int x be a normal variable, like a static variable, let's make it into a dynamic variable. Okay? What that means though is we are going to have to create, and I'm intentionally going to not put a destructor so far. We'll come back to that in a second. But I'm going to go ahead and allocate it dynamically. So I have to say something like x gets new int. Remember, new operator and the type. And then I'm going to go ahead and do my assignment afterwards. But I do need my dereferencing operator because remember, now this is a pointer. And I need to go to wherever that pointer is pointing to, which is where my variable I created is at, and then put the 10 in there. Okay, so I need to do that in both the default constructor, but also the other constructor here. Except in this one, instead of setting it to 10, I am going to set it to whatever is in I. Okay, and now comes the question about the copy constructor. Okay. Let's go ahead and comment out the copy constructor for now. Because like I said, you get one by default, which right now will actually be doing the same thing I was doing before. In fact, here, let me Control C my way back to the code before I change anything. I want to show you something really fast. Okay, we run it. Still runs. Let me get rid of the copy constructor and show you that it will still give me 1075. Bam, you see that? So what that is saying is that we are actually getting a default copy constructor that is making a deep copy, right? So now going back to what I was coding with the dynamic variable. All right, we have our dynamic variable. We have a 10 in here. We have our other variable here for the one to put the parameter. We're assigning it to that. And we're not going to put a copy constructor, okay? And I'm going to comment out the change here and just let it run. Actually, I'm going to need to use either the arrow operator or I'm going to need to use my dereferencing and parentheses, right? So one or the other, but I'm going to mix match so you can see you can do either or. Okay? So as you can see, why are you complaining, code? Ignore. It's broken. Yeah, it's just code being weird. Wait, no, there is an actual problem. What am I doing? It's not the object itself is not dynamic. It's just the variables is dynamic. So actually here, I just need to put asterisks to all of these and not need to worry about anything else. Okay, just to make sure that they're reference. Okay, so you can see now that I don't have a copy constructor. I have this with a 10. I still have this with a 5, and this also has a 5, right? However, let's go back and uncomment this line and rerun it. This time, you can see that we're getting 7.7 instead of 7.5. Now, what is this happening? Well, in this case, because we're using again the default copy constructor, it's making a copy. Quote unquote, is making a deep copy of the variables, but here is the issue. The variables are no longer static, they're dynamic. So all you're copying is it's still running this code. In fact, if I uncomment this now and rerun it, it'll compile and run and still give me the same output. Because this is literally what's happening. It is copying the value of x, but guess what? X is no longer like a static variable that actually contains the data. It's just a pointer, right? It's just an address. So it's copying the address of this here into here. And so we are getting the shallow copy issue that we had with arrays. That's basically what's happening. So when we go ahead and change 7 here in A2, because A3 is just literally a copy of the pointer, it's pointing to the X from A2. And you also are creating, with this line of code, a memory leak. You can prove that by running the Valgrind. And seeing that you have your memory leak here. Well, actually, we have a lot of memory leaks because we don't even have a destructor so far. But let's try to put a destructor and see what bad thing's going to happen. I'm not even going to run it with VS Code. I'm going to run it directly here because I want to show you. Oh, well, that's assuming it runs first of all. Semicolon. I'm going to get, where is it? I thought I was going to get a sec fault, but I didn't. Okay, sure. Still, even though we didn't get a sec fault, which I'm pretty sure this gives you a sec fault in some systems, is you're getting this invalid free, right? And it's telling us that it is happening at line 15. So basically the destructor line 25 is calling it. So line 25 is probably just the end of main. Oh wait, no, that's just a creation of, oh, it's saying that the object that was created there, block was allocated there, right, okay. Yeah, so the destructor is causing this, as this should be. Why? Because, well, A, we have a memory leak here, and B, we're calling the destructor whenever an object goes out of scope. So when A2 goes out of scope, it calls the destructor, and it goes ahead and it deallocates its X. But guess what? Our A3, because we only copied the pointer and we created a memory leak there, it's now pointing to A2. So we're actually calling delete on the same thing we just deleted. So it's a double delete, which can lead to a segmentation fault. But furthermore, you still have the memory leak problem, which is why, in addition to the errors, in addition to the errors, I would expect to have a memory leak, but Valgrind says there's no memory leak, but I'm pretty sure there is. Interesting that Valgrind says there's errors, but it doesn't detect the memory leak, because here is where the memory leak is happening. In fact, let me run the debugger on this. That's crazy that it doesn't detect it. Yeah, so we're doing the copy constructor, so we're just changing the pointer. I know. Oh, okay. Yeah, no. It is correct. There is no memory leak. Because guess what? Forgot to say this. When you're running the copy constructor, you're running like any other constructor, right? We're dynamically allocating variables here and here. We're actually not dynamically allocating anything in the copy constructor, right? So there's never a dynamic allocation for A3. And you're just setting the pointer to A2. So there's no actual memory leak. It's just bad and ironic because we now have A2 and A3's X pointing to the same location. So it's a shallow copy, okay? I stand corrected there. So how do we fix it? First of all, in your copy constructor, if you have dynamic variables and you have to dynamically allocate them just like with any constructor. Second of all, you don't want to copy the pointers. You want to copy the contents of the pointers. So you want to do something like this and this. And so now if you run it, it'll, well, let me remove the pointer. There we go. Now we run it. We actually have the correct output. Okay? And if we check Valgrind, we should not have any memory leaks or errors now. Okay? As you can see, no errors, no memory leaks. So in short, what the copy constructor is whenever you want to create an object out of another one. This is very useful. Also, there are scenarios when you pass a object by reference, or sorry, when you pass an object by value in a function call. When you do that, you're making a copy of the object, right? So we all know that when we have something like function void foo and that function has a parameter, and we're calling that function, and we say something like foo5. Well, this was more obvious because it's a parameter, but like if we add something like int g gets 5, and then we said foo_g, what is happening here is we are not passing the actual variable g into function foo. We're passing a copy of that value. So we're taking what is in g, which is a 5, and we're copying that. I don't know what that parenthesis is there, so there's semicolon. Okay? So it's important to make that distinction because, I mean, hopefully remember this 1 through 5, right? You're not passing the actual variable. So if in here I go in and say x gets 10, if I see out x inside the function, it'll say 10. But when I go back to main, it'll still contain the original value of g, which was 5, because we passed a copy, right? So when you pass an object in a function by value, that same logic is happening. It's making a copy. And guess what? It's actually using the copy constructor. So if you're not aware that the copy constructor is being used and you are using dynamic variables in your class, you may run into issues with memory leaks, with that shallow copy issue with you have variables that are pointing to the same one, to the same memory location, which can then cause free errors when you're deallocating, when you're destructors at the end, which can cause crashes and other nastiness. So the moral of the story is, if you're going to be using dynamic variables, which you are, then you have to make sure that if those variables, or if those classes we're using the dynamic variables are being passed into functions by value, that you have a copy constructor. In fact, this is part of what is known in programming as the rule of 3. And in Wikipedia, you can Google rule of 3, wiki, and then click C++ programming, and I'm going to leave a link in the description below, but for now I'm just going to share it. So here's Wikipedia, rule of 3. You will get to see that there's also rule of 5 and other things, but that the rule of 3 makes the 3 things that you should have as a rule of thumb whenever you're using dynamic variables. And that is that you should have a destructor, a copy constructor, and a copy assignment operator. Now, we haven't gotten to operator overloading yet, so we will revisit what copy assignment operator is, but in short, you have the same situation here when you're doing something like this. So let's say we have an A4, or actually here, let's just say that we have our A1 and we're assigning A3's value. Okay? When this is happening by default, you have the same problem. It just makes a copy of the contents of the class, which in this case, if it has pointers, it just copies the pointer address. It's not actually allocating new memory and then copying the contents of what the pointer is pointing to. So we are going to have to do the same approach as we did with the copy constructor for the assignment operator. But for that, we're going to have to do overloading, and we'll get to see that in a future video. So I guess just for now, I'll be aware until you get to that video, that which will be soon. It's like 2 weeks or something from now, or in terms of video count, about 3 to 4 videos from now. But or actually, I stand corrected. I think it's the next topic after this one, because we swapped them. It used to be templates first, but now I think it's operator overloading right after rituals. So maybe you'll get to see it in the next video after this, maybe, or the one after the next one. Okay, but yeah. So this rule of 3 is very important, because otherwise you don't know that you have these bugs that can be pretty nasty to fix, and you're getting this undefined behavior and occasional crashing and other nastiness. Okay. So just remember the rule of 3. When you have dynamic variables, you want to have destructors because the memory leaks. copy constructors and copy assembly operators. So other part of rule 3 is saying that if you use one of these, then you should always have all three. And because destructors are required to avoid memory leaks with dynamic variables, that pretty much means anytime you use dynamic variables, you're going to need all three. But I suppose in weird scenarios, you have a copy constructor that you can't use the default one. It's probably because you're using pointers again. So yeah, basically just always have all three and play it safe. Okay, so that's all I'll say about that. But we will revisit that when we talk about operator overloading. Okay, so 25 minutes in, we finished copy constructors, and now we can actually talk about virtuals. Okay, to talk about virtuals, however, I am going to, like I said, introduce you. Actually, first let me back up this code that we just did. There we go. Let me propose the following code, and I think I'm going to do that code. Yeah, I'm going to do straight on VS Code, because otherwise I have to copy it over. Okay, so let's yeah, we can leave a lot of this in here. So let's go ahead and leave all this in here that we have. So we got the same class A, but now let's go ahead and make a new class. Okay, let's call this one class B. Okay, now class B is no ordinary class. It is the inherited class of A. It has the inheritance from A in it. Okay, so yes, we are coming back to talk about inheritance. I told you a lot of these topics, they come back. So the last time we saw inheritance, we saw the power of it. You know, great power comes with responsibility when it comes to things like diamond problem and multiple inheritance. But we just saw the overall power that you can take a current class and you can expand it. The same still applies when you're dealing with dynamic variables. However, there are some risks that you're going to, have when dealing with dynamic variables that I would like to explore, because I'd rather you screw up now than in the real world, right? We want to see these risks. We want to step into the danger, burn, step in the fire, get burned a little bit now so that we can see and we can avoid it in the future. Okay? So, my class B is coming from class A, but I'm also going to have in class B an additional pointer. So my class A is amazing. I want to expand it. So I'm adding more variables. It's a pretty standard thing that happens with inheritance. So my class B is going to have a Y pointer. And of course it needs to have a constructor. This time I'm going to make one with a default parameter so that I can set it initially to 0, or here let's do 2. And then let's set, let's dynamically allocate Y. And then let's set it to the contents of I. Okay? Like that. Now I'm going to leave it like this just to save some space. But because it's already getting kind of big, and I'm also going to do that up here. Like that. Okay? Just to conserve space so that we can show more screens content. Okay? All right. So we also need to have a destructor for B so that we can avoid memory leaks. So we can have our delete Y. And then we should also have a copy constructor, but for now I'm going to skip it. But it'll be the same idea. You update this one. You have to update it now, I suppose. Whatnot. Okay. All right. So this is all relatively good. I don't know why this is. Oh, this should have a dereferencing operator. But yeah, other than that, it should be good. Let's just run it. Make sure it compiles. Okay. So where do I go? Where do I go from here? Let's go ahead and actually just let's make a couple of pointers. Okay. So earlier you saw me getting confused between doing something like a2.x versus a2x, right? And that's because for a second I thought that the A object we had was dynamic. This is not dynamic, but if we make it dynamic, all we gotta do is make this into a pointer and then dynamically allocate it, right? And here we can call the constructor that we want or just not call anything. So in this case, I'm gonna call it, I'm gonna pass the 5, okay? I can do the same thing with B. In this case, I'm gonna pass a 10. Do note that I should do something here with the A, otherwise I'm gonna call the default one. So if I didn't want to call the default one, maybe we have a second parameter that has like a 4, and maybe that gets passed in right there. Okay, that makes it do something neat. So now here, that's probably gonna be now. So I need to pass something else in there. So maybe let's do 9. Okay. So now this B will contain a 10 in the Y and a 9 in the X, right? I mean, we don't have to guess it. We can just bring it out. Okay, and I can also print out the A, just so we can see that too. All right, so crap. I keep forgetting they're dynamic, so we gotta put them asterisks. But at least you can see the addresses are all different. That's kind of neat. Okay, so we got a 5 from here, and then we get the 9 and the 10. I don't know how I feel about these being backwards, but that's okay. All right, so this is all good. It all works as expected, but here's where things get a little scary. Okay, what happens if I do the following? And I do have a separate video on casting that I will make available, and also just the word abstract in general. But I still want to bring this up now, which is what happens if I go in here and I have two objects, right? I have A and I have a B. Let's make a couple of pointers. Okay, so let's make another A pointer. We're gonna call this APTR, and let's make another pointer from B. Call this one BPTR. Now these are not objects. These are not. There's no memory allocation for these. These are just pointers. In fact, all pointers are technically static here because they're made at compile time. The 4 pointers exist already. So what happens if I do the following? APTR A. This is saying make this pointer point to the object from A, right? And so now if I rerun these codes, but instead of A, I put in APTR, and if I do the same thing for B, so I do BPTR, we will see that the exact same output will print out. 5910, 5910, and they're both referencing the same object, right? No memory leaks either. Well, yeah, no memory leaks, so I don't have anything there, but here, let's triple check it. Oh, definitely memory leaks. I thought I had the delete. Delete Y, delete X. Why am I getting memory leaks now? Definitely lost. That's a lot of memory leaked. That's not the issue I wanted to show you, but I guess that's a different issue. Then I have to see what's up with this. Okay, so our A is calling delete X. That is not the issue, and our B is calling. Let's run it through the debugger actually and see what's up. Okay, so from there, okay, I pushed the run button. Hold on, let me rerun it. Keep forgetting to put the breakpoint. Okay. Oh, it's not entering. Why is it not calling the destructor? Oh. Yikes. I guess I need to get some sleep here or something. I forgot that these are dynamic objects now. So you have to delete them. So you have to delete A and then delete B. So of course there's memory leaks. Jeez. Okay, my bad. I apologize for that. But we should be okay now. All right, we're okay. So, okay, back to the real issue at hand here. All right. So we have an A and we have B. And we have an APTR that points to A and BPTR that points to B. These don't generate any memory leaks on their own. They're just pointers, and we are deallocating the A and the B, and there's only one object of each so far. Okay? Now, let me go ahead and propose to you the following, okay? I have a pointer of B, okay? I'm gonna go ahead and change this line of code to A. Now, this is already being underlined as like a red flag per se, but more importantly, I want to bring up this situation of being able to point to an object, a class that's not yours. Okay? So I could do this, and I could also do something like this, right? Now, what does this mean? Like, what does it mean to do something like this and to do something like this? What I'm saying in this line of code, let's start with the first one, is an object that is really a B, because this is B, I am making a pointer that is A point to an object that is B, okay? Doing so, I am fooling, per se, the compiler after this line of code into thinking that APTR is actually pointing to an object of A when it really is pointing to an object of B. In this line, it's the same situation but reversed. I have an object of A and an object of B. And I am telling the compiler, take this object of A and have it point to an object of B. Now, one of these is giving me this underline and the other one is not. And if I compile it, one of them is going to yell at me. Or at least I think it will. So we are getting yelled at by this one, but not this one. This one's like, that's cool. It's cool with me. Why? Okay, what turns out is that what happens after I fool the compiler into thinking that this B is really an A? Well, let's understand what A and B are, right? So A has X in it, right? And then B is technically has an entire A in it, but it also has a Y in it, right? A little Y. So in the line of code, I am saying I have pointers. I have a pointer, and I have B, right? Actually, I have this. And what I'm saying is, if you look at the line, is I want APTR to have the same constants of B. So I want APTR to point to that same object. But APTR is a pointer of type A. Why is this okay? Because when you make it like tunnel vision into thinking that it's an A, it's only going to see the inside contents that is an A. And that's perfectly fine because B contains an A in it. So there's no inherent risk to you accessing something that doesn't exist, right? All B's have an A inside of them. So if you fool the compiler into thinking a B is an A, there's no harm done per se, because there is actually an A. You just can't see the leftovers. You can't see that there's a Y as well, which is not so good, but it's not like going to cause a problem. The other way around is really bad. Why? Because if I have an A, so let's copy and paste this. If I have an A, which is currently being pointed out by A, and I want to point it now with a BPTR, what I'm saying is I want, instead of this being an A, I want the compiler to think this is a B. Now, why is that the issue? Because B's don't just have this X in them, they have a Y. So what happens if this B tries to access the non-existing Y? Well, really bad things are going to happen, because your program's going to crash, or it's going to just go out of bounds and access invalid data, kind of like when you access an index out of an array, right? Because in memory, class variables are stored in like an order, usually the order they appear in your code. So, you know, there might be here an X, and then there's a Y for an object of B. But for an object of A, there is only the int X. And then there's other stuff, which is not yours. It's the operating system giving it to potentially other programs, or merely just garbage data. So if I try to access a Y in this scenario here, I'm going to access basically garbage, which is a bad idea. In the scenario where I have a B, but I think it's an A, that's okay, because you're still only accessing the content of the X, which are there, so it's no problem. You just can't access the Y, which, whatever. It's like, sure. So this is a bit of an issue, because, well, first of all, you can see it won't let you compile one of them. But second of all, the one that does compile, what happens now? Like, what does this mean now? This means that I can't really access the Y part of it, right? It still works, but I just can't access it. And so if I try to delete it, so instead of calling the delete, you know, I'm gonna leave the delete B here, or actually delete A, because I'm no longer messing with A. But if I, instead of calling delete B, I call delete APTR, here lies the issue. Delete APTR is going to try to delete an object of type A, but really APTR is holding an object of type B. So let's look at the debugger and see what destructor gets called. Bam, the A destructor gets called and no B destructor. And as a result, you have a memory leak. Right there. So, what have we learned here today? We have learned that we can fool the compiler into thinking that an object of a child class is an actual object of the parent class. And therefore, it's calling the destructor of the parent without calling the destructor of the child, therefore causing memory leaks. Furthermore, suppose that I want to change the pointer back from APTR to, like, let's just say I have another pointer here, or BPTR. Let's say I want to switch it back so that I can then call delete on BPTR. Well, now we're going to run into that issue from earlier, that it says you can't do that casting, because it's like, whoa. this is an A, and now you want to make it into a B, but a B contains things that an A doesn't. And you're like, well, yeah, I know, but like, I actually did this earlier. It's fine. This is really a B. Like, chill. The compiler's like, no, I don't know that. I don't trust you. It's like, no, I'm not letting you do this. And so this you can solve with what is known as a dynamic cast, which is what the other video is going to be posted on. I'll just write it here really quickly, but you know, please check out that video for details on why this works and how it works. So I can do what's known as a dynamic cast, and then actually this is a B, cast to a B, and also the star should be after, not before. So that'll solve that issue. Or at least it should. Runtime must have polymorphic class. Ooh, why? BPTR dynamic cast B. Does not like that at all. Cast this pointer from an A to a B. Source type is not polymorphic. I don't know why. I don't remember why. It's been a while and I haven't gotten to that video yet. So I haven't played with this, but now I'm wondering why. Maybe when I add this virtual magic, which I was going to show you to fix the other issue, this will fix itself. So we'll revisit that later, okay? But let's go ahead and finish here. So how do we fix this issue that it's calling the wrong destructor? Well, the magic is going to come in the form of a virtual. So I want you to go in here and add the word virtual. So now, if I rerun this code, in fact, here, let me run it one more time without the word virtual so you can see that we still have the issue. Where did you go? Hold on, I accidentally closed this. There we go. Okay. Run it. We have memory leak. So now, if I go in here and I add the word virtual, so now, I don't have a memory leak. So, and if I run it with a debugger, you will see that it is calling the correct destructor, which is B, and then technically also A, because it has called both destructors, right? The parent and the child. First it calls the child destructor, then the parent. So first B and then A. So what is happening here? Like, why is this dark magic working? And also wonder if this is still giving me the issue now. Let's go back and uncomment this. Maybe it doesn't like the fact that this is on the same line either. I don't think that would make a difference, but. Yeah, so now it doesn't complain actually. So that also, like, it was predicting myself, like, yo, what are you doing? You know, add virtual to that. So, okay. So the other issue has resolved itself by adding the word virtual, okay? So A, you can see that it fixed that weird error, but also B, it fixed primarily the error with the memory leak. Before I explain virtuals now, I'm gonna swap over to another example, okay? So you already saw one issue, quote unquote. So now I'm gonna show you another issue within the same sort of idea. So the idea right now is it's calling the wrong function, okay? So now let us go ahead and create a function inside of class A and call this function foo, okay? And we're gonna, inside of this function foo, we're gonna see out A. just so we can identify it. Okay, and then within class B, I'm gonna go ahead and also make a function foo, which would in theory override the function, and it's gonna see out B. Okay, so now at the bottom of this, I'm going to go ahead and do something like C, or not C, I'll just simply call, do I have an inline? Yeah, I have an inline. So let's just go ahead and say a foo and b foo. And you'll see A and B get printed out as expected, right? But now we have our APTR, which is a pointer of A pointing to an object that's really a B. Which function do you think is going to get printed out? A. Again, the same problem as before, but in a different way. The problem being that the compiler, because you made this B object up here be held by an A pointer, the compiler thinks it's really an A. And so it's not just the issue with variables, or sorry, with the destructor, but with any function. It's always going to call functions from the class that it's pointing to. And similarly, if I go ahead and add this magical word of virtual, it actually fixes the problem. As you can see here now, it's a B. Okay, so now that I've shown you both of the examples, let me explain as to what the problem is and why it's being fixed by this. For that, I need to explain what the difference is between compile time binding and runtime binding, okay? So this is really important that you understand, and this is by no means the last time that you will see this. You will see this in pretty much a bunch of courses if you're taking CS courses at UNLV. In fact, when you get to compilers, which is one of the cornerstone courses of the degree, there's a lot of people in that class that seems to struggle with virtuals, and so they told me to make sure that you guys get this, because like it will come back, and I don't want you to feel like you're struggling with this. That's why I'm trying to really emphasize is what the problem is and not what the solution is, okay? So first of all, because I want you to know this by all names, there are three names to represent the same thing, which is this compile time binding, static binding, and early binding, okay? There's this in comparison to what is known as runtime binding, which also has two alternative names, which you should be aware of. Again, I'm not trying to confuse you. On the other hand, I'm actually trying to give you all possible names for the same thing, because not everybody's going to use the same terminology. And I don't want you to get lost just because of some terminology issue, okay? So, let's talk about this binding nastiness, all right? So, C++ by default does what is known as compile time binding. What that means is that in an effort to optimize your code, when you're writing a class, and that class has functions in it, and variables and other things, but primarily looking at the functions, it doesn't store the function code for every single class you make, like that is inherited from a parent class. So what I'm saying is, I think you already understand that, like, if you have two objects in C++, like let's say you make a class A, A1, and then a class A, A2, like, so you have two objects of A, it makes sense that while each of them have their own independent local variables, so like if my object of A has an X in it, if I make an A1, I know that that has its own copy of the object X, right? And if I make an A2, it also has its own copy of the object of the variable X, which could be an object too, but I'm just getting the idea, okay? So if you have also a function foo, it makes sense that with variables, because they each have a copy, they should have a copy of them. But it makes sense to like not have a copy of the function code itself, on each object of the class, right? Because like it's literally the same code you're running. It's the same math or whatever. So like if function foo is just going to take x and multiply it times 2, you don't need to store that memory that represents the code to do that operation on every single object of A. So you're like, here's a copy of foo, you get a copy of foo, and you get a copy of foo, and everybody gets a copy of foo. No. One copy of the code foo is enough, and then just remember that foo is a function of A, so everybody can actually reference and look it up. Okay? Now this lookup is going to what's known as a lookup table. Okay? And this table contains all the functions in the code, including foo for A. So whenever you say something like a1 foo or a1.foo, it's looking up in the list of functions that A has, finding the foo, and running it. Okay? Now if you do inheritance, and now you have a B that inherits from A, and you call foo, it's going to look up in A to find out foo, unless you overloaded it unless you overrode it with a new function in B. And that's why this is an issue when you're not dealing with pointers. The issue comes with pointers because now it thinks that it's an A and it's looking up in the wrong table. It's looking in the A table when it should be looking in the B table because you fooled it. So that's because at compile time, it needs to know what the type of the object is. And then you might be saying, well, it does because you wrote the code. Sure, but now let me tell you how I could modify this code so that it's impossible for the compiler to know. Let's say that I write the following piece of code. bptr let's just comment this for now, or just leave it like this. So aptr, let's make the pointer on its own line. And now let's go ahead and say aptr gets A, aptr gets B, and put this in an if statement. Okay, sorry, for some reason I wanted to put colon, so I was like, nah, parentheses. I'm like, nah, don't put anything. Okay, so here we have an example of the same as before, but in this case, we're using user input to decide whether aptr is going to hold a pointer of A, which is actually an A here, or it's going to hold a pointer that actually points to an object of B, which is what we've been doing so far. And so you can see now that if I go in and put in a 0, that it's actually holding an A. And if I go in here and put in anything other than the 0, it holds a B, right? And it's all working because I have this virtual. But if I remove this now, you can see that it's always going to give us A. If I put a 0, it gives us an A. But if I put anything other than a 0, it still gives us an A. And that's because it's have this magical virtual word in there, okay? So in this case, the compiler can't know at compile time what aptr is holding. So when it's looking at this line, all it knows is that aptr is a pointer of A. So it makes the deduction that it must be pointing to an object of A because it's a pointer for A. So I mean, that's a pretty not a malicious thing to do. So you're like, okay, how do we solve that? Well, clearly compile time binding is not going to get you out of this because you don't know at compile time in some scenarios what you're actually binding the function to the object or the callee. Okay? So the alternative is to make that connection at runtime. In other words, to look up what function to use only at the time you actually see that piece of code when you're executing the code at runtime, running the code, runtime. And then you go and look up, okay, what is this object really? Is it an A or is it something else? well, it's an A pointer, but it's actually a B. And it was like, okay, it's a B. So let's go look in the B. However, instead of making everything runtime, which some programming languages do like Python, C++ defaults everything to compile time unless you explicitly say, nah, make that function be something you do at runtime. And it'll do that, but it'll also tell you basically, hey, there are some risks doing this, so just be aware of that. So it does potentially bring up some issues that could happen at runtime versus compile time. Compile time catching the errors is good because you catch them before you even send somebody the code. You're compiling it. Runtime means runtime errors, which are not so good because you don't see the error until it actually happens and the end user is actually using the code, right? That's why debugger and quality control are important at that point. So that's known as runtime binding. Also dynamic binding, also late binding. You can see the word early and late kind of obvious because once it compiles, once when the code's already running, it's too late to do anything. Static versus dynamic, you can think of static like static variables, dynamic with dynamic variables, or compile time versus runtime. Whatever makes it click in your head, it's all good. So what the virtual function does, it does that. It defers a function to be put under the runtime binding table. So virtuals, whenever you add virtual to a function, it puts it in a special table called the B table. And so now, if at compile time it sees a function like this, it puts a little marker saying, hey, don't do any binding now. Defer this to runtime, and we're going to put this foo function in the B table so it's readily accessible there. And so now, when the code is running, and you hit that line of code, and it sees a foo, it's like, oh, this foo is part of the B table. So it's part of that special table. So we actually need to see what this is being called upon. It's like, oh, is this really an A or a B? Oh, it's a B. Okay, so now we go to the B table, and we find that B foo. And yes, both versions from A and B will be stored there. Even though I only have the keyword virtual on the first one, so I only have it on the parent, this will propagate to any of the derived classes as well. So all instances of foo, even if I have a class C that inherits from class B, will always be virtual. Once virtual, always virtual. Okay? So that's really the power of virtuals. Another powerful thing with virtuals is the diamond problem. So with the diamond problem, you can actually do what's known as virtual inheritance and resolve issues where you have two of the same class because of the multiple inheritance. So I wish I just had some code up. Well, maybe we have some code from when we did the diamond problem. Let's see if we find that code. Class B. Yeah, this does look like it. Perfect. Okay, so let's save this one. Okay, so we're bringing up code 4. So this is why I like keeping the code. We have it. Yay. Okay, so now we have this massive amounts of code. I hope it compiles. Oh, it does not compile. Class C doesn't have a field named Y. Okay. Oh, ooh, hold on. That did not paste right because there's like weird stuff going on there. Okay, that's probably Y. There we go. Okay, so we have some code. We have a class A, we have a class B, we have a class C, which is a multiple inheritance, and then I don't even know what D is doing. Let's get rid of D. Oh wait, we don't have a technically. Well, there is a bit of a diamond problem because we probably have two variables shared, right? Actually, I think this is just normal multiple. It's not a diamond problem at multiple inheritance. Let's see if maybe. No, this is the best we got. See if 3. Ah. This one's better and it's shorter too. At this point, we could have probably coded it ourselves, but now. Okay. So we got class A, class B, and then we got a class C. And now let's just go ahead and make a class D that inherits from class C. but also from class A. Okay, so now we have a diamond problem issue because we have two instances of A, right? So not quite the nicest looking thing, but that's okay. All right, so if I go in and try to access, let's see what A has, an X from A. So I say cout A dot X, or sorry, no, wait, actually, hold on, let's make a D. So let's make a D, and then let's say cout D dot X. This is going to be ambiguous, right? Because we have the diamond problem issue, right? Ambiguity, it's all ambiguous, blah, blah, blah. And it's true, it is ambiguous. Because there are two instances of A in D. There's one from here, and then there's one from C, which has an A in it as well. So we know that one of the ways that we can resolve this is that we can actually say something like, get the one that's actually coming from A. Or I guess, actually that goes in here. Yep. Nope, it's still not liking it at all. What about this one? Okay, so it's just not like it at all. Direct to class A. So anyways, I guess you get the point that like it's a mess, right? Well, check it out. Here's one of the things that we can do. Virtuals isn't just limited to doing virtual functions. You can do, like I said, what's known as virtual inheritance. So I can go in and I can throw the word virtual in front of this inheritance. And actually, I think maybe I should do it here. Or maybe I have to do it at the level A. No, this one works fine. So yeah, because by then you already have issues there. So yeah. If I go in and add the word virtual when I'm doing my first inheritance here, then I'm getting a quote unquote virtual copy, or not a virtual parent per se. And so what that means is kind of like, that was a little harder to explain, but like you're saying I want A, but I'm only going to want one copy of it. And I don't know yet if this is like the copy. Wait until you see the code. And so here, when we got a D, and we see that we got an A from here and an A from here, because they're both virtual, it's like, oh, you only want one of them. So it just takes you one of them. And it resolves the ambiguity, but more importantly, it resolves you having two of the same class in there, which you probably don't want. So I know that might be a little bit kind of just like, hey, this works, but really, hey, it works, and it's the best thing to do. Although really you shouldn't be having these issues in the first place, because the diamond problem is just not the good thing to have. But at least know that you could use virtuals to get you out of a spot in a hurry. Okay? So I just wanted to bring up that advantage of virtuals with inheritance. So we talked about virtual constructors, virtual inheritance, a little bit about pointers, and let's talk about the this pointer. Okay, so another thing that is really important to understand when it comes to how things are organized in memory is when we have the following. So let's have a class A. So it's a brand new class A, and it's going to have an int x in there. It also is going to have maybe a double y, and then maybe an int z. Or actually, you know what? Let's throw in there, have something here. Let's make it one more class then. We'll call this class G, and class G is going to have just a random int D in there, okay? So we're going to use composition, and we're going to put a G in here. GG's. Okay? So in memory, how this is being stored, like I said, is you have your class A. So an object of A is typically going to have an X here, and maybe a little bit more space, two of these technically, for a double Y. And then it's going to have the G in there, which has its own space for the D. So this is G, which basically also has D in it. And so every time you make an object of A, so let's say you make another one down here, and there's some memory in between, other stuff, it's going to look like that. If you make an array of them, they're all going to be nice and stacked together. To be able to locate the member variables of an object, so like if I have a function foo or whatever, and this function foo maybe sets the value of y to be equal to 5.0 or 5.2. If we have something like that, and so I have in main something like says like AA, and then I say a dot foo. You might be asking yourself, like, how does foo know which y it needs to change? And then you're like, well, obviously it needs to change the y of this object here, right? Sure, but like, how does it actually keep track of that? And you're like, well, that's just some dark magic that's happening. And yes, part of that is some dark magic that's happening that you learn in 219 and other classes like 370. But for now, what you should know is that in addition to having basically the details of the class, like, you know, that we talked about with like the function storing the lookup tables and whatnot, whenever you make a function call, you pass in a couple of things. Number one, if you have parameters in the function call, so like let's say there was an int y in here or something. Well, actually here, let's just 5.4 or something. And let's just say that there were two parameters here, like an int y. Well, we already have a y, darn it. Let's do a t and a g and a c, okay? So we have something like that. When you're making that call stack, they call it call stack, you're passing in your parameters. But remember, there's only one instance, unless you're doing like virtual, there's only one instance of the code, right? So this code needs to have a reference to know who the object is that's calling it. Is it A1, A2, A3, A50? Which one is it? Now, how do you keep a reference in C++? Pointers, right? So, in addition to passing the parameters when you do a function call, it passes a pointer, which is the reference to the object that called it. We call this the this pointer. Okay? So in short, two things are passed to functions when you do a function call that's part of a class. The parameters of it, because I mean the parameters you need them for the function to work, or there might be none. But then it's just like some hard-coded function. Imagine like a getter function, like a get x or get y. That has no parameters, but it still needs to access class variables. And then there's the second thing. It needs a way to access the variables that belong to the object that was called upon. And that is done in the form of the reference that is a this pointer. So addressing wise, the first spot, and I bet you this is something they're going to ask you when you get a 326 or a 460, the compiler's class. They're going to ask you about, like, you know, what is the first thing? What on the first address? You usually use like the at. You know, what is address 0 of the call stack of the function call? What does that contain? That is going to contain a reference to the object itself, which is that this pointer. Okay? And then after that, it may or may not contain additional stuff that's passed in, like the parameters. If it has parameters, it'll be here. And they'll be in the order they appear. So if you have some function called void bar, and it has an int y, int z, and then a bunch of other stuff in there, it's going to be like y, z, and so on. Those parameters are going to be passed in. Okay? Now, when is it the only instance that you don't need to have a reference to the object that gets called, but is still a class function? Think about it for a second. You always need it, but there is one special case when you don't need to access like the member variables of an object that calls it. Little moment of pause, you think? And the answer is static function. Okay? Now, we don't really use a lot of statics in here, but they do exist. And as a refresher, when you have something like a static integer, static variable, that means that there's only one instance, right? So whereas with, like I was saying, each object of like A, so let's say A1, A2, A3 has like copies of the variables, right? So like memory for them. And there's only one copy of the functions, right? And it's in that lookup table, unless there is some virtual stuff going on. But even then, there's only one copy per class. It's just that it's not linking them until runtime. Well, with static variables, so if there's a static called like, I don't know, ID, there's only one single instance of it for the entire program. And then anybody that accesses it will access that one. And they will all share it basically together. Can be useful for things like track of counts or just things to have as a reference that are strictly related to a individual object that you have. So in this case, that's a static variable. There's also static functions. Static functions, just like normal functions, there's only one instance kept in the program really. But the big difference is that static functions can only access static variables. If you try to access a static variable if you try to access a non-static variable from a static function, it'll give you an error. Let me show you that really fast. I think it's worth showing. So I have here some stuff from the other one. I just simplified it. So let's go ahead and let's make a static variable. Static int ID. Actually, you can't initialize them. You have to initialize it as start of the class, even if it's private. The syntax is always trippy for this, but I think it's going to be that. I think that's okay. Nope, it is not okay. So I guess I have to put the word int. Yeah, okay. So it's kind of trippy, but yeah. So when you declare a static variable, you have it like this. And so now if I go in here and I make A1 and A2, each of these has its own x. I don't need to prove that to you. I think we've established that. But what I do want to prove to you is that if I say something like AX gets 10, and then I say A2X gets 12, and then I say cout A1X, that is going to print out 12 because it's one shared variable. Well, X is not a static variable. I meant to say ID. But I guess that proves to you that the non-static variables have their own copies for each object. But if we do it with the static, then you get a 12, right? Because we're, A1 has a 10, but then when you change it to 12, it's changing the static to 12. So then they all have that. So like, if I print out A2.ID, they're both going to have 12. It's going to look like 1, 2, 1, 2 together, but yeah. Okay? So now if I go in and I throw in a function, it's the same thing. If I try to modify a static function a static variable, that is not a problem. The problem comes in if I try to modify a non-static variable. See the error. Invalid use of member AX in static member function. Non-static member reference must be relative. See? So it's yelling at me that this is non-static. As long as I get rid of that, I have no problem. Why is that? Because a static function can be referenced like this. I can say food like that without specifying an object. And that code runs. Just like I can also modify ID, by the way, by saying it like this, without a specific object. That's the power of statics that allows you to do that. Okay? So, because statics do not need to modify, or actually can't modify any of the member variables, there is no need to pass a reference to it. So the this pointer is not needed. So, again, if you get asked this in the future, with a non-static function, the first piece of memory in your call stack is going to be the reference to the object as a this pointer, and then beneath that's going to be the parameters. Whereas with a static function, there isn't going to be a this pointer. It's just going to be parameters or potentially nothing if like the function is just like some cout hard-coded thing, or just modifies the static. Okay. Now you can always actually look at what the this pointer is. You can say something like, you know, well, you have to do it in the function. So like, let's go ahead and add a function to this. Let's say void bar this x gets 10. So now I'm going to go ahead and say a2 bar, and I'm going to cout a2.x, and you will see that it contains a 10. So all this is doing is basically saying I am referring to the x from this object. So I'm actually accessing that first parameter that I'm talking about that gets passed in. So I'm actually accessing this right here. And you can, you know, be explicit about that by putting this in front of it. I guess too many this. This is automatically added by the compiler. So that's why you don't really regularly see this. You know, I mean, in fact, there's no reason to put it when this is the same thing. But if there's an ambiguity issue, so like let's say you have a variable here called x. If you have it like this, then you have a problem, right? You don't have anything in that x. In fact, it's uninitialized. So a solution to this could be one, yeah, you could use the class name and resolve that, which is what we've done in the past. But another thing you could also do in theory is you could say this x. And this is actually more appropriate per se because you're talking, when you see this, you know that you're talking about a member variable. Okay? It's also a nice way to be able to print out what the location of the object is in memory, and you can get pretty hackish with that. So like, if I make a function, we're going to call the function hacks, and it's going to return a pointer. Or actually, yeah, not even that. Let's just go ahead in here and go ahead and see out the address of A2. This is the address of A2, right? Notice what the address is of A2.x. You don't need these, but I'm gonna put them anyways. Let me add some line feeds to make it easier to read. Notice that it's the exact same address. So the this pointer is also going to be the address of the first parameter. You can get, like I said, pretty hackish about this because I could actually print out the value of t, which should be 5, right? So if you see a2.t, you'll see that that's equal to 5, right? Well, I can also print that out by doing the following. Address of that plus 1 Yep, that seems right. And now I'm going to dereference that. And you get a 5. See that? I am doing some really nasty stuff there, but it works. So in other words, I start by getting the address of X, and then I'm going to add to that address 1, because I know this is an integer, so just 1 out of pointer arithmetic, it's adding 4 bytes. And then dereferencing that, and I'm actually accessing the second variable using the first variable's name. Now, I'm just going to do this for fun. Let's make it private. Look at that. I'm accessing a private variable now. If I did a.t.t, see out that, this would give me an error and say, hey, this is a private variable, you're not allowed to access it. It's private within this context. But, getting a little quote-unquote hackish, I am able to access it, no problem. Furthermore, let's go ahead and run this again. Look at that. Not only am I able to access it, I'm able to modify it too. So I'll just show you how to modify a private variable. Goes back to day 1 when I was talking about public and private. I said it's an honest man's lock. It's by no means a secure thing. There are ways around it. Pointers are one of the ways that you can get around that. So by no means do you think that like you putting something private is like some cyber secure thing. No, it's more of like to not accidentally access things you shouldn't. But there are ways around it, and you shouldn't be doing it because why is it private in the first place? But know that it's, you know, where there's a will, there's a way. Anyways, enough about that. Really what I wanted to get to was talking about this. So that's the this pointer. Okay. So going back to my list of things, I have abstract classes and I have casting. However, I do have videos on both. So I know you're looking at this and it's over an hour 15, but the casting and the abstract videos together are about an hour long. So I will let those cover those 2 topics. One more thing I'll say before I end it is, let me show you one more thing here. So with virtuals, by the way, this whole craziness you're doing with virtuals that I showed you, that falls in line with polymorphism. And I think that they will be mentioned more in the casting video, in the abstract one, on why it's polymorphism. But one of the big usages of this that you're really going to like benefit from is that you can make an array of pointers of a base class, so the parent, make it point to a bunch of childs, and achieve the ability to have a array that is otherwise a homogeneous array be a heterogeneous array that can access that can store different objects of different class types as long as they have a common parent. So that's very, very powerful. And I'll let those videos explain that. But one thing I want to show you is I can actually make what's a class that is like an abstract class. And an abstract class is going to be a class or just a virtual function in general. You saw what virtuals do, right? Like you saw how it solves that issue. But one of the things I want to point out is a virtual function is not required to be completed when you create it. So if I make a class like this, I mean, actually, hang on, I think, let me remove virtual. Does this give us an error though? No, it doesn't give us an error because there's a body, but let's just put it like that. So this doesn't give us errors until we actually call it, right? If we call it, then it'll give us an error and say like, hey, you haven't defined that function, so like you have a problem, right? It's inaccessible. Well, actually, that's the different issue. Hold on. The inaccessible issues elsewhere. Okay, so the VS Code is just like exploding. But if I run this here, you can see that we get some undefined reference error. So like the linker is having issues here probably. It's like you never define this function, so it's like freaking out. If I had the word virtual, yeah, I get the same error. But more importantly, yeah, there we go. Okay, so compare this. So I have to, unfortunately, I have to run it with the terminal. So normally this, you know, if I don't have a function, or if I have a function but the function has no body, as long as that function does not get used, everything is fine. You can get away with it, not putting a body to a function, right? But if you have the word virtual in there, all of a sudden it doesn't let you really compile it. And it says undefined reference to B table for A, right? So remember the B table thing I'm talking about? And so you might be asking yourself, well, okay, why do I want errors? Well, here's the cool thing about virtuals too. Sometimes you want to make a class, a parent class, that's more of a blueprint for derived classes, but you don't want to let the people using your code to create objects of that sort of parent class. Now, what do I mean by this? I'll give you a practical example. Say you're making a video game, and you are making a list of different packages, like classes of characters, like a medic, a soldier, or like you're playing Battlefield or something, like medic, soldier, sniper, or engineer. Okay, so you might want to have a common class for all of them, just called player, but you don't actually want to create a player because each one, they have to have a class associated to it. So it is useful to be able to have these sort of blueprint classes, but not allow the people developing the later code to actually create an object of that type, such as the case is here. So you make these functions that are sort of templates that have to be filled in into the derived classes, but for now, you sort of leave them like in a sort of to-do list. So that's what I'll say for now. But when you watch the pure virtual functions video, which we'll talk about pure virtual functions, which look a little bit different, and that's one of the weirdest syntax you'll ever see, we'll kind of explain that further, okay? But I think that's enough for this video. So today we learned some pretty important concepts, particularly when it comes to virtuals and how they can solve a lot of our issues, but also bring some risks associated to it. We also talked about this pointer and how call stacks work and how functions are able to access the member variables of the class object that the function is being called from. We also, well, I always say we, but there's nobody here but me, except my dog, if you could hear barking. But yeah, I also talked about copy constructors and how the rule of 3 is very important to follow and how you have to be careful about this. See, all the things today, when you think about it, even virtuals, like in constructors and inheritance, today's like really, if I was to say the TLDR of today is, fixing problems that you didn't even know you had, but you would have run into otherwise. Copy constructor, because you would have run into problems with dynamic variables and passing objects into class like as parameters by value. The idea of virtuals in terms of like of having a parent pointer point to a child pointer and vice versa, because you probably hadn't ever done that yet, but at some point you would have done it and you would have had this issue where it's not calling the right class. Diamond problem you did see, and today I show you one of the other ways that you can fix it. And then of course memory leaks that you would have run into because again you're doing nastiness with pointers. So really today's day is like how to fix things that you didn't even have to worry about, but now you're gonna have to worry about them, and you're like, oh no. So yeah, but that's not to say this is really powerful stuff. Other languages, like I said, like Python, everything is runtime, so there's no such thing as virtual because everything is virtual. And well, you might be thinking like, oh, that's automatically better. It's not that one way is better or worse. It's your approach to how programming should be. So when things are runtime, you defer errors that you could catch now to runtime, which makes them potentially harder to catch, but you have flexibility. If you do everything compile time, then you can catch more errors, but you lose some flexibility and you lose some capability. So the middle ground is like this, where you can actually make stuff runtime, but you have to explicitly call it that way, so that you only put flexibility where you want to put it, and not have it where you don't want to put it, because otherwise you could run into errors. Okay? So, like I said, take it easy with the virtual stuff, but definitely watch the other two videos so that you can complete this. And remember, they're going to come back. So please ask me questions, because virtuals is one of those topics that I feel is important to know more than you think now. So don't dismiss them. They're your friends. They're there to help you and to solve problems. They're the problem solvers of C++. So use them. All right. Thanks for watching, and I'll see you next time. Take care.